only 20 minutes before class, so I'm going to make a quick video for the solution and hopefully have enough time. Let's see. Okay, anyway, so our first problem here, problem 1, we were to do an analysis problem. We have this bar of 1050 steel with a diameter of 2 inches and had a groove that was cut to a depth of 0.125 and the radius was 0.3. We have 50,000 pounds, both going completely reverse, so tension and compression, and the thing is not rotating. And there we had 95% reliability desired and 750 pounds, and we want the yield and fatigue safety factors. And if finite life is predicted, we want to estimate the life of the thing and then plot a point on an SN diagram. So here we go. We start with the geometry, and the depth, was 0.125, so you subtract 2 of the depths and you get 1.75 from the 2 inches is the diameter that we're going to use based on what's in the caption of the figure. So the D over D is 1.143, which is close to 1.15, which is one of the curves in there. And the R over D is close to, it's a 0.1714, which is close to 0.175. So looking up quickly in here, we see we have 1.15 and 1.75 is right there. So I estimated with a little bit below this and a little bit to the left that I got 1.79, right? And your mileage may vary, but you should be careful to get the correct numbers. So I got 1.79, and then from figure 620 or from an equation, I was able to get my notch sensitivity, which is 0.849. And let me look that up right there because I want you to be familiar with using the tables and the figures of the book. So here we go right here. And here is the figure in the book. Whoops. Trying not to lose my page there. And I said that the radius was 0.3, which isn't on this figure right here. So, and then our ultimate strength was, well, we haven't found it yet, but it's 90 KSI. So it's just below this line right in here. And like I said, our radius was 0.3, so we're kind of be dipping down right in here. So I said that my notch sensitivity was 0.848, right? So pretty close to like here's 0.9, so it's kind of like just below my the 0.85, right? Coming back into here. So combining that with our stress concentration, we're able to get a fatigue stress concentration of 1.67. For the stresses, well, that's just going to be the load divided by the area. So we got plus or minus 20.79. We multiply that by the stress concentration, fatigue stress concentration, and so we get 34.72 KSI. Now for the strength, like I said, I looked this up for this steel, and we get 49.5 KSI yield and 90 KSI. Our laboratory, the prime endurance strength is 0.5 of that, or 45. For our surface condition factor, Ka, I have 2 different values because this is the 10th and earlier edition, but in the 11th edition we have different A's and B's, right? So there's your A and your B values right in there. For the KB, which is the size factor, we equals 1 because this is axial stress. And the loading condition or the loading type is axial, so that's 0.85. And maybe I can do a little bit quick. I don't want to spend a lot of time on this, showing where these first came from. Like I said, class starts pretty soon. But anyway, we start out with Ka from equation 618, and we populate it with the A and the B. And I believe because this was hot rolled, we used here 11 and 0.65, right? Yep, raising the ultimate strength to that B. And then for this one, we say axial KB is equal to 1. That's the size factor, KB. And then for the loading type, or the loading factor, right here, we have for axial 0.85. All right, so let's see where we got the other ones. For the temperature one, so for this particular when I used the 11th edition, and I got the average between two values, because there was a, I think there was a 700 and an 800, so we needed to get the in between value, and I didn't put it back into the equation. Let's see what the differences would have been. I think with the equation, the temperature factor, no, the temperature factor here, I should have adjusted for that. Let me see what happens here. Pause. If I put that in there. Instead, so the 11th edition doesn't have the temperatures the factor as a table. They just have it as an equation right here. All right, so here's the equation for that. Let's see that there's a slight difference. We got 0.8995 in the 11th edition. We have 0.881. We'll see. I'll take a look and see what that does for the overall. So KF, which is the miscellaneous factor. One that I missed was the reliability factor. We wanted 95. So to get 95, we went to here. No, that's not it. Yeah, 95. And we get 0.868. 0.868. Okay, and then like the miscellaneous factor, which isn't used in the 11th edition, is 1. So here is what I get for my endurance strength. I get like 17, almost exactly, from the 10th edition. I had 17.45, but I don't think I had the correct one in here. So let me see. The value I actually got was 17.41. So it's going to be slightly off what I have right there. Okay. So for a safety factor, which I sent in an email because I didn't see this in the book written simply this way. If we just have simply simple loading condition, you'll see in the next class that we're going to have a more complex loading condition. But a simple loading condition is simply the endurance strength divided by the repeated stress. Therefore, and we get a 0.49, right? So obviously we are not infinite. And it was like 0.5, right? So there was only a slight difference right in there because of the difference that we had in the surface condition factor in this case. I didn't put the temperature factor in. So we estimate the life. First we look up this F from figure 618. And now in the, by the way, in the 11th edition, we could actually use an equation they have in the book for this. And but this is the figure that we're looking that up in, right? And we go based on 90, and we could see that we're just below 0.86. So that makes sense, right? Just below 0.86. We can also, they were nice enough to do a curve fit right here. And so I didn't do it yet, but I think we should get pretty much the same answer right there. So there's the curve fit equation with the ultimate strength. Just one thing to remember, if the ultimate strength is below 70, you just use 0.9, right? That says it right there. Okay. And let's see. So we multiply that F times the ultimate strength, and that's going to give us that point that's right at the 1,000 cycles. That's so helps create the little line. And then so for the parameter that we use, it's really sort of the coefficient that's in front of the equation that looks like this right here. That guy. That's like a curve fit for our SN diagram, right? We want a line that looks like this right here. So there's the curve fit. So we have that first point. That's where that F times SUT is coming from. So that's what we're using that for. And you know, it's slightly different for the 11th edition. Well, once again, this would be ever so slightly different because I did the temperature factor is a little different. And then we get B, which is the exponent in that curve fit, and I get the negative 2191. And then, okay, so we plug in this in, I get 38,000 cycles. All right, so that's my predicted life. And if I use the other endurance strength to get the parameters A and B, and by the way, that equation is just simply flipping this equation around and solving this way. So, and I don't know what the AR necessarily says. We usually, in the other editions, they go rev, so that means completely reverse stress. But I don't know, I'm not sure what they mean. I have to look in deeper read. And the yield safety factor, notably, is 1.43, because we should check that, right? Because it might, you know, the yield strength is less than the ultimate strength. In many inductile materials, it could be significantly less than the ultimate strength. So it might actually yield the first time, which rendering it maybe perhaps not useful. But once again, what's a little strange here is that we were using the fatigue stress concentration in there, but neither here nor there. It's a good thing to check. So the 11th edition, as you see up here, are in red, and here's where that plot point would be for the 10th edition one, right? Obviously, it's really going to be not that much different right there, but it's good practice to have the SN diagram. Now, on the second problem here, this is a design problem, and so we have to kind of work backwards, and our goal is to design a stepped shaft, which is to go from two different diameters with a little fillet, and we want it to die at 100,000 cycles if we can. And it's subjected to a fully reversed, non-rotating torsional load in the range of 400 to 500 Newton meters. I made it just a little bit easier, right? Because we could go back and make the design of the thing, and then go back and change what the load is, so that we could say, okay, well, let's try to aim for 100,000. We're really kind of sort of testing out the whole system right here. Maybe if we had a rig and a test rig, and we could measure that 100,000 cycles and see how close we got. The shaft is to be made from this 1060 steel, quenched and tempered. And I think I decided to make it machined. I think that's what I decided. Anyway, the operating temperature is 550 degrees Celsius and reliability 50%. So just the standard reliability is 50%. So that's what we're keeping with. And we want to find this diameters D1 and D2 and the fillet radius R and the torque, right? So we can, that gives us like a little bit of grace. And you should also use, I say that later right here. You should use table A17 for preferred sizes. So we don't want to go weirdness, right? So we have to kind of first do a stress concentration assessment without knowing everything. So we have to make guesses first. So the strength, we get that easy enough, right? 800 megapascals is ultimate strength. And so I get my SE prime, and I think I used, and I used the 10th edition everywhere for in here. So if you used the 11th edition, you'll get something else. But I think everybody is going to get something a little different because it's a design thing. Maybe not. I mean, maybe there's one particular one that works out pretty well. But I kind of tried to make a problem that was a little bit more open, right? That you could kind of choose some things yourself. I just want to see which one I used, and it looks to me I did machined, right? So you know you're going to machine the thing. So that was my logic in applying that surface condition factor. For the size, I'm just going to keep it 1 for now because I don't know how big the thing is. I know it's in shear, so I used the 0.59, right? It's in torsion. That's the loading type. The temperature, I must have set a temperature that because I don't remember saying. Let's see, what did I say? The temperature was 650 degrees, right? So that's something that I looked up. All right, so come on. There you go. And reliability was equal to 1. and F is equal to 1. So I get a preliminary endurance strength. And so I can get the life now, right? So I have the ultimate strength, so I could get that F from figure 618. And then I get that F times SUT. I can get an A, and I can get a B. And now I can get the stress is going to have, what stress is necessary to for this thing to fail at 100,000 cycles, right? Just because I got the A and the B, I can go backwards and get the stress. So now I do some geometry right here, and I want to go backwards and get a d over d of 2. Why? Because I go to that graph and I see that's a line, and I see 0.1 is a pretty good one to line up with. I can figure it out. That's kind of like my rationale. It's sort of in the middle of the road. In a lot of design things, there might not be like a really good reason for why you're doing the thing. But I picked 2 right here, and I picked 0.1 because that just seemed like a good spot, 1.45. And you're like, why? And I'm like, well, why not? It was an available one. All right, so I assumed a 2 millimeter radius, and so I got a Q, a shear Q. Now remember, you got to use the one that's based on shear of 0.85. And I got 5 minutes to class. I really should end this right now. So I think I will, and I'll just pause it and we'll come to class. I'll see you in class and be done with this and post the video as soon as I get done with class. It took too long to talk. That's all right. It happens. Okay, back on to this. And okay, so I found from this preliminary decisions, right? So I just made some decisions that I was going to make the d over d equal to 2 and the r over d equal to 0.1. So I got that stress concentration, and then based on a 2 millimeter assumed radius, I get a 0.85. And I'm just picking this because it's in the middle of the road, right? This is some of the design. You just have to make some decisions, and then make sure that you remember to come back and reconsider them if it turns out to be something that doesn't make sense. So based on that, I'm able to work out backwards because I have the known stress that will cause a failure at 100,000, and I'm able to get what a diameter is going to be. I also assume 450 newton meters. Why? Well, I was told the range should be between 400 and 500. So here's what the diameter came to, which is really close to 25 millimeters, which is kind of fortunate. So what am I? I'm 25 millimeters. Okay, let's see where that takes us. And so I used the d over d ratio of 2, so I made it 50 millimeters, and then with that 0.1 that I had assumed in the beginning, got 2.5 millimeters, and it all seemed pretty reasonable. I get a stress concentration that I had predicted. And that 2.5 millimeter versus the 2 doesn't really change the shear, the shear notch sensitivity. So I kind of kept that the same. I want to revise the strength though, because now I know the diameter, so I can revise what that previously assumed 1 for the KB is going to be. So I need the, because it's not rotating, even though it's circular, I need to get an equivalent diameter. So I get an equivalent diameter of 9.25, and I plug that back into equation 620 to get my size factor. So the size factor is not that much. It's only like 90.9773. So like, what is that, like 2.3%, something like that? It's not a lot. And it updates my endurance strength to 119. What did I have before? My initial endurance strength was 121, right? So with that, I want to revise my applied load. So I have my applied load. I'm going to get A right here, and then B. And if with that, with 100,000 as my thing, as my number of cycles, I have that the stress should be 210.4. right? So that just didn't change it much. And so now the torque, no, the torque required to cause this failure is 466. So then I would summarize my on a sheet of paper there at the very end that all of this information up here, right, that the diameters and the radius and what my load is, 467 newton meters. And hopefully that would come out to maybe I say 470, right? So because I once again, I don't want to be too specific and make it sound as if that's exactly the load that would require exactly 100,000, because I know that it's not going to be the case. The last part of this that I had you do is I had to make a sketch, right, that shows a scaled sketch. At least I meant to imply that it should be to scale. Let's see. What was my phrasing in here? Summarize resulting with a dimension sketch, right? So I would expect you to make a scaled sketch in that. I'm going to do it in SolidWorks, but you didn't have to. The reasoning behind this is a lot of design comes from drawings, comes from checking out and seeing, does this make any sense? So let's take a look and see. And I don't think there'll be any kind of problem with this, but I'll do it anyway. So I'm going to make this, I think I'm already in US units, yeah. I'll make this the 2-inch part of it. Oh, I meant to make it in, it shouldn't be in US units, right? So I should be in, I'm going to change this to I'll change it to millimeters. Boom. And yeah, we'll double check this. So this should be just 50 millimeters. I don't know why we had such a 50 millimeters, right? And I'm going to just extrude this to, doesn't really matter to me how far I make it. I'll make it 50 millimeters, right? So to be kind of, that long. And then on here, I will make a 25 millimeter. So just to see, what does it look like? I mean, all right, well, that's actually pretty small. Wow. Yeah, I guess that makes sense as a 2-to-1 ratio, sure. I'll make this 50 millimeters too, so it just looks okay. And then we're going to put in a fillet. Put a fillet right in there, and that fillet should be 2.5 millimeters. How come it's not giving me a preview here? I don't know. Let's see, did it work? There you go. All right. Now the reasoning behind doing this is as a sanity check to try to see, okay, what does this look like? I don't want to just provide numbers without like checking the thing out. Like, okay, sure. So let's see. I want to save this somewhere, and I will save it underneath. I have a SolidWorks directory for these assignments. And sometimes I save the thing here, sometimes I save it in a folder. I think I'll just save it down here. So this is F21, ME370, homework 10. And it looks like I already had something in there named that. That's interesting. I don't know why it was coming through there. Homework 10, problem 1, that's why. All right. We'll go problem 2. All right. And then I'll make a drawing of it. Why not? It's not that hard to do. Make a drawing. And if you have something short like this, make it into an A-size drawing. Is usually landscape or portrait. Either way, landscape works. You don't need anything bigger than that. I use B-size drawings for a lot of stuff, but this A-size drawing is pretty good. So, and we don't need a particular. We don't need other views. You only need one view, right? So you don't need to see something down the length of the thing. And I think for the time being, I will take my scale as 1-to-1. I think maybe it makes more sense to go 2-to-1. No, that's a little too big. That's kind of huge. I think 1-to-1 is fine.
it'll be a little small little thing here. We go, boom. Yeah, 1:1 looks fine. And see, you don't need to make this right here, and you don't need this, but I ain't gonna kill you to make this other view, but I would make this smaller. Doesn't need to be that big, so use a custom scale. 1, 2, yeah. So somebody could see what the thing was that you're making, but I wouldn't necessarily. Like, this is kind of an unnecessary, but it doesn't hurt. And then put the smart dimensions on it, right? So we want to go here to here. Whoop. It's not so smart. Okay. Yeah, I guess I'll pick this guy right here. And I prefer to keep the dimensions to the outside. And notably, I'm in inches right now, so we got to fix that. Let's see, we'll scale that. And then here, boom. All right, so let me fix my thing here. Turn this into millimeters. Boom. All right. Yeah. Sometimes I like to put these to the outside. They look just a little better. Maybe like this. Depends on what the arrangement is. And there you go. 2.5. I kind of liked it where I had it before, but I got to remember which way to go. I think I had to go like that. No, like that. There you go. 2.5 fillet radius, and then change your sheet format, right? So edit the format. I don't know why this thing always turns out to be the wrong size. I'm actually going to copy that and drawing number F21 HW10. Good enough. And then up in here, like right where the thing is, a little better. There you go. Problem 2. And then put your name in there. So all caps is good. Deal. Sometimes I put my initials in there. And then what the date is. 11 19 21. It should have been a 19. I don't know why I didn't get a 9. There you go. Some of this other stuff isn't necessary. I would almost get rid of this. I don't know why we always have to have this stupid proprietary thing. It's not like some kind of secrets or anything. We might want to keep these. All right. And I don't know if we have in these annotations sketch, can we trim entities? Oh, did it wrong. Trim entities, use that to cut that. No, did it wrong again. Trim entities, use that to cut that. Ah. No, I guess I have to do the other way around. Okay, sorry. Cut that using that. There you go. Same thing here. Cut that using that. There you go. Pretty much everybody else. The material, we might want to even fix this. All right, there's not even a spot to put that in there. So I guess we have to put an annotation. Sometimes what I'll do is I think it's stuck on the trim. That's why. Let me see. We have one material, right? And what did we say the material was? We had a material in the beginning, right? So we said that the material was going to be 1060 Q&T at 650. That's made my life hard. AI. Whoops. Come on in there. AISI. Why aren't you letting me type? There you go. AISI 1060. Whoop. Q and T 650. And I don't have the degree symbol stored here. Why? There we go. 650. I'm messing this thing up left and right. don't know what happened here. I think it has something to do with the margins. Yeah, I don't know where those are. Yeah, I need to fix this. Maybe some other time. I can't figure out why. Why can't I move it? There, I'm moving it now. Okay. Why can't I move it? Oh, what's the move? What's this snap? All right, we're gonna leave it there. We're done. All right. So anyway, and then make a PDF out of this, right? So first off, save it, and then make a PDF out of the thing. So print, and we're gonna go. I'm gonna go Adobe PDF because I have that, and a page set up, and I think landscape already. Preview it. Looks good. Hit the print, I think. No, this guy, print there. There you go. Okay. And I'll put them into that same directory in here. I don't know. Yeah, there you go. And then I will take a picture of the whole thing, and I'll put him into my solution. Boom. Make this the right size, center it, and then make it into look like a piece of paper. And I like to do that right there. So there we go. We're done with homework problem. I did a lot more information than you probably wanted. But the idea here is if you're going to design something, you should make a drawing of it. You should make a sketch. And in the process of doing that, you might find out that it's like, wow, that didn't make any sense at all, right? Making a 3D solid model of it, it's even better than just making a sketch and a drawing. Just get to learn a lot more from it. There you go.